Alright, here we go. So I wanted to go through a couple of actual examples. In the last video we just talked through some conceptual stuff and got through some ideas. Let's go ahead and look at a couple of examples now. Alright, so this first one is talking about a particle moving in a straight line, position relative to the origin given by such and such, where t is the time in seconds. Alright, so here we go. Find expressions for the particle's velocity and acceleration and draw sign diagrams for each of them. Okay, so first we're going to find the velocity, and we know that the velocity is the derivative of the displacement, so that becomes 3t squared minus 3. Okay, now if I'm going to draw a sign diagram for that, then I'm going to find the x-intercepts. So the x-intercepts, I'm going to make y 0, so v equals 0, add the 3, divide by the 3, I'm going to get 1 equals t squared, which means I'm going to have x-intercepts at positive 1 and negative 1. If I put a 0 in here, so just to kind of show you what I just did, I went 0 equals 3t squared minus 3. I added the 3, so 3 equals 3t squared, and divided both sides, so 1 equals t squared. Square root both sides, got positive and negative 1. If I put 0 in, I get a negative number, so there we go. Now it does say that t is greater than or equal to 0, which means that most of this actually doesn't even really matter. Okay, so we're going to actually take off anything that was negative there, and we'll just kind of go like this. And here's 0. So we'll start at 0. That's not an x-intercept, so I guess I probably shouldn't have put a hash mark there, but that's the idea. Starting at 0 going forward. Negative before 1, positive after 1. So what that means is between 0 and 1 seconds, it has a negative velocity. It's moving to the left. After 1 second, it started moving to the right. At 1 second, that's an x-intercept, so you have a 0 velocity there. So that's when it's changing from going to the left to the right. Okay, let's look at acceleration. Acceleration, of course, is the derivative of velocity, so we get 6t. And so, of course, with that, again, I'm going to start at 0, and then no matter what value I put in for t, I'm going to get a positive number, which means I'm always having a positive acceleration. Okay, that would explain why the velocity goes from negative to positive, because if I'm initially going to the left, a positive acceleration would cause it to slow down and then start going to the right and speeding up. So to find the initial conditions and hence describe the motion at this instant. Okay, well, we talked about most of that already. It's going to the left, has an acceleration, a positive acceleration, which means it's actually slowing down. The other thing is that if I were to put 0 in for t here, then I would get positive 1, which means I start to the right of the origin. So putting all of that into play, if this is the origin, I'm to the right of the origin, I'm moving to the left and slowing down. Okay, so that's pretty much anything I can say at this instant. All right, describe the motion of the particle at t equals 2 seconds. Okay, well, if I put 2 in, then I get 8 minus 6 plus 1, which is still positive. So I'm going to get a positive 3 for my position. So I'm still to the right of 0. Okay, so here's 0. I'm to the right. At this point, though, I've passed the 1 second mark, so I'm moving to the right. I still have a positive acceleration, and so I'm speeding up. Okay, now depending, you could actually give all those details. I could be saying that I'm speeding up. I could actually find the actual velocity at that point. If I put 2 in here, I'd get 3 times 4, which is 12 minus 3. So I would have a 9 centimeter per second velocity. And so you could get more detailed. You could write down a specific acceleration rather than just 6t. And so, of course, you can get some details there. All right. For letter D, find the position of the particle when the changes in direction occur. Okay, well, the only change in direction is when I stop going to the left and start going right. So that would be this 1 right here. So that would be at 1 second. That's the time, though. I want to know the position. So I need to put that 1 into the equation. So I'd have 1 cubed minus 3. So 1 cubed minus 3 times 1 plus 1. And so when I put all that together, I get 1 minus 3 plus 1, which is -1. So I'm one space to the left, so I'm at -1, one space to the left of the origin. Okay, so just kind of thinking through various ideas. Draw a motion diagram for the particle. You know what, we're going to skip that because I think that it's boring. Really all that is you're drawing a number line and you're saying, okay, well, here's my 0 at time 0. We talked about before at time 0 the position was at 1. So at time, so I could put my 1 down and I'd say, okay, here's time equals 0, and then at 1 second, where am I? Well, I'm at -1, so there's my time equals 0. Then I've got -1, so that would be time equals 1, and then you put down a different point for each point in time. So this is when it's turning around, so you can kind of connect it if you want. But then you put the various points down and show the location on the number line, so you can get a visual idea of what's happening to that particle. It goes to the left and then comes back to the right. Okay, for what time intervals is the particle's speed increasing? Well, because it says speed, then that means that the velocity and the acceleration need to be in the same direction. The velocity is always increasing because I always have a positive acceleration. But when is the speed increasing? Well, it's only when they're both positive. So for time greater than or equal to 1 second. So from that on and on and on. All right, and what is the total distance traveled in the time from 0 to 2 seconds? Well, from 0 to 1, it traveled a distance of 2. And then I think at t equals 2, we found a location for that, right? We said that when it was 2, it was 8 minus 6 plus 1, which was 3. So it was over at 3 at time equals 2. And so therefore it went from -1 to 3, which would be 4. So 2 plus 4, which is a total of 6. All right, so that's pretty much the gist of it. So we've got a total distance. Remember, distance and displacement are different. If it's displacement, then it's just where did I start, where did I finish, which would only be 2 centimeters. But given that it's asking for distance, I need to calculate all the path that the particle traveled through. Okay, so that's an example. Why don't we look at one more just for good measure? In fact, why don't you try this one on your own? Okay, go ahead and pause it, work through it on your own, and then I'll go through it a little bit more quickly this time. Well, hopefully you've worked this out for yourself now. So we've got find velocity and acceleration functions. So the velocity is going to be the derivative of what we had up there. So putting in standard form would be -6t squared plus 12. And the acceleration, of course, is going to be the derivative of that, which would be -12t. And the 12 goes away. Letter B is find the initial conditions. So that means I'm going to put initial conditions is time equals 0. So if I put 0 in, I have that s of t, so s of 0 equals -1. If I put 0 in here, I'm going to get v of 0 being 12, and I'm going to get the acceleration at 0 to be 0. So interpret their meaning. I am one space, 1 unit, nope, it's in centimeters, 1 centimeter left of the origin. I am moving at a velocity of 12 meters per second to the right, and the acceleration is 0, so not accelerating. All right, so there you go. There's letter B. Boop. Letter C, find the times and positions when the particle reverses direction. Okay, so reverse direction means that it's stopping going left and starting going right, or that it's going right and then stopping and turning to go to the left. The way to find that is when v of t is 0. So we're going to set 0 on the line here with v of t. 0 equals -6t squared plus 12. And so obviously there's numerous ways to go about this, but if I factor out a common -6, then I end up with t squared minus 2. And so t, of course, equals plus or minus square root of 2. Now if that's the case, we know that t has to be greater than or equal to 0, and so really the only value here is root 2. So at root 2 it is reversing direction. The position to get that, you're just going to take the root 2 and put it into your equation. So s of root 2 is equal to 12 times root 2 minus 2 times root 2 cubed minus 1. So I've got 12 root 2 minus 4 root 2, because I took root 2 squared, and that would be 2. So I multiplied it by the 2, and I still got 1 root 2 left, and then minus 1. So final answer of 8 root 2 minus 1 is my position. If you got a calculator, then you could go ahead and work that out, but chances are you won't have that. So you can just leave it in this 8 root 2 minus 1 centimeters. All right, and then letter D, at what times is the particle's speed increasing and velocity increasing? So in order to do that, we are going to need a sign diagram for both of these, the velocity and the acceleration. So if I do velocity, I do know that the particle reverses direction when the velocity is 0. The velocity is 0 is at 8 root 2 minus 1. So somewhere over here, this is 8 root 2 minus 1. So before that, when t is, for example, 0, it's going to be positive. And then as t increases, then my velocity is eventually going to become negative, because this is eventually going to be more than 12. So that's velocity. The acceleration is going to always be negative. So the answer about the velocity increasing is never. And when is the speed increasing? Well, anytime when t is greater than or equal to 8 root 2 minus 1, the speed is increasing. Now, you may look at this negative and say, well, does that really make sense, Mr. Bauer? It can't be increasing at 8 root 2 minus 1 because it's 0 there. Well, it is 0 there, but no matter how much time you look in the future, it then has increased. Increasing is an interval, and so we're looking for an interval, which means that an interval goes from point A to point B. It doesn't matter, starting at this specific time, 8 root 2 minus 1, it doesn't matter if I go 1/100th of a second in the future or 1/1,000,000th of a second in the future, it's going to increase. So therefore, over this range, starting at 8 root 2 minus 1, that's when the speed is going to be increasing, because it'll go up from there. Okay, so I think that's enough, and you're welcome to watch some more videos if you like.